Let's look at some numerical experiments with convolution operators on L2 set. So we start with certain examples of convolution operators. We will look at the spectrum of the operator A, and we will also look at the finite sections. Our first example is the forward shift, and we already know what the spectrum is going to be. But let's see. Okay, here we see it. This is the unit circle, and that denotes the spectrum. The little red star in the middle denotes the origin of the complex plane. So obviously the origin is not part of the spectrum, so the operator is invertible. Now we let little t run around the unit circle and see how A upside down head of t is running around the spectrum. And in that case, it's running around the unit circle in exactly the same orientation. Remember that for the forward shift, A upside down head of t is just t. Okay, no big surprises up to here. And now the next thing we do is to look at the finite sections of that operator A and their singular values. Here we go. Well, to be honest, there is not so much to see. You can see that on the vertical axis at x-coordinate 0 and x-coordinate 1, we have a little pile of dots running up, and these dots run from n equal to 5 or 6 up to 100. And that's exactly the little n, which is the size of the finite sections you're looking at. And for each one of these n, you see in horizontal direction a plot of the singular values, which is a bit boring here, because for each one of these an matrices, you have one singular value equal to 0 and n minus 1 singular values equal to 1, and that's what you see here. Well, obviously we have a splitting property here. So one singular value is running into 0. It's actually sitting at 0. And all the others are staying away from 0. Recall that this is the property that characterizes stable regularizability. And one more thing to say here. The number of singular values that run into 0, in this case 1, coincides with the winding number of the curve that we just saw, this one here. And by winding number, I mean the number of times the curve was winding around the origin. So here you can see again what we just observed for the forward shift. The spectrum is the unit circle, and it was traced out exactly once surrounding the origin in mathematically positive orientation exactly once, and that's what we mean by saying the winding number equals 1. Okay, and then here we have this n axis where n was running up to 100, and for every such n we were plotting the set of singular values of an. And if you look at this finite section an, then it looks like this. And you easily see that you have a one-dimensional kernel. You could just, the singular value decomposition would just move up all the rows by one position and then getting the first row into the last position, which is this rotation thing. And then you have your diagonal matrix, which has ones on the main diagonal up until the penultimate entry, and the last one is 0. So that's how you see that you have n minus 1 singular values equal to 1, which gives you this pile. So every dot of these is in fact n minus 1 dots on top of the others. And with this 1, 0, you get this pile, where here actually 1 dot is actually just is really just one singular value. Now here comes our second example. It's the fish operator, and there's your fish. So this is exactly the spectrum. And now let's see how a upside down head of t is running around the spectrum while t is running around the unit circle. Here we go. Obviously the winding number is again 1, so we are expecting for the singular values of the finite sections to see a splitting again, where again 1 singular value is running into 0 and all the others are staying away from 0. Well, let's see how that goes. Now this is looking much more interesting. So again we see n running up to 100, and so in the last row we see 100 little dots, where in fact the smallest one seems to be very close to 0 and the largest one is at about 20. So let's summarize here what we saw for the fish. Okay, so the winding number is 1. And that 1 means that 1 singular value was running into 0. You can see that here. And all the others are staying away from 0. Maybe let's zoom in. Now let's see how far away is the rest staying from 0. So the other singular values seem to stay to the right of that green line. Okay, the location on the horizontal axis was denoted by epsilon in our chapter 4. And here, if you look at this, epsilon seems to be a bit more than 2. And if you remember correctly, then that means the norm of the pseudo-inverse of the limit, so of the operator A itself, must be about 1 over 2, so half. And this blue line here is another interesting line. So all the singular values seem to stay to the left of that blue line. And we know that the maximal singular value marks the norm of the operator, in this case an. And these seem to converge to 20 or a little bit more. So the norm of A seems to be about 20. So if we look back to both examples, in both cases the sequence of finite sections is not stable. So in both cases you have singular values running into 0 or even sitting at 0. So in the first case your more Penrose is stable because they are exactly 0, so you can ignore them if you switch to the pseudo-inverse. And in the second case you need epsilon regularization with epsilon around 2, and then all these singular values sitting on the red line will turn into zeros, and then your more Penrose invertible and stable. So in both cases the operator itself is invertible, but the sequence is not stable. So remember that even in the new Polsky theorem that inclusion did not hold. So invertibility of A does not imply stability. The other way around, yes. This way, not. Roughly speaking, the reason for the sequence not being stable is, and this is particularly for convolution operators, that the winding number is non-zero. And you can see it. We said that the winding number is telling you how many singular values are running into 0, and you would need a 0 winding number in order to see them all staying away from 0 and thereby get a stable sequence. Now let's look at some third example. Let's see what that is. Okay, and we can can see still the same fish, but apparently the origin is now outside. So the winding number is now 0. This curve is not winding around the origin, it's just passing by. And now we should see a stable sequence. We should see 0 singular values running into 0. Let's see whether that works out. And indeed, everyone is staying away from 0. Very nice. So in this third example, we translated the fish by essentially just changing the 0th Fourier coefficient a little bit so that the main diagonal entry of my convolution operator gets translated, gets changed. And then 0 is now outside, so the winding number is now 0. And that means no singular value is running into 0. Everyone is staying nicely away from 0. Now this is stable. Whereas the previous example was stably regularizable, and our first example was more Penrose stable. Should we do another example? Yeah, come on. Here's number 4. Let's see what we have. This looks very nice. Let's count how often this curve is surrounding the origin, which is the little red star. So here we go. 1, 2, 3. So I'm counting 3 windings or 3 rounds around the origin. So you should see 3 singular values running into 0 and the rest staying away. And I think that's exactly what we see. So here's what we saw in this fourth example. By the way, here is the sequence of Fourier coefficients. Yeah, and that's the image of the function a upside down hat. It's surrounding the origin 3 times, so you've got a winding number of 3, and that should lead to 3 chains of singular values running into 0. The first one is already a little bit visible here, and then there is a second, and here is clearly a third. And let's see whether the rest is really staying away. It seems so. And this lower bound epsilon seems to be about 1, so that the norm of the pseudo-inverse of A is 1 over 1, which is also 1. And let's see what the norm of A might be. It's about 7. And what do you think this sequence is? Is it stable? No, of course not. It's not staying away from 0. Is it more Penrose stable? No, it's not. Some of the singular values are going into 0 without being 0, but it is stably regularizable because your singular values are staying, well, partly in this blue interval here. That is going from epsilon to infinity. Well, actually 7 is enough. And some other singular values are in this green interval that goes from 0 up to our cutoff point Cn. But for this cutoff sequence Cn, you could just take the third singular value of every matrix An, and then that goes to 0. And now let's look at 1/5 and last example. And here we go. This is actually not looking good because the curve seems to run through the origin. Let's see. whether that's happening. Yes. So it's running through the origin, which means our operator is not invertible, which is actually not a big deal, but in fact one can show that it's badly not invertible. It's not even a Fredholm operator, as you say. It's got an infinite dimensional kernel. So, I mean, we cannot even count the winding number, so we cannot even say how many singular values are running into 0. And the fact that the kernel is infinite suggests that infinitely many singular values are running into 0. Let's see whether we can verify that here. Difficult to say because you would just have to let the code run longer. But from looking at that, you couldn't really draw the line where you put your epsilon and say, obviously the rest is staying away from this. Or maybe we should let it run a bit longer. So let's take a closer look back at our 5th example. Okay, so we observed that this time the curve is passing through the origin, which is very bad. It means the convolution operator is not invertible, and in fact it means it has an infinite dimensional kernel. We wouldn't even know what winding number to count here, and in fact we cannot count the number of singular values that go to 0 here. So this time I let n go a bit higher, actually until 400, but you still wouldn't know where to draw the green line. That was fairly obvious to draw in the previous examples, but not so here. And if you want to count how many singular values are going to 0, then you could zoom into the lower part of this image and would probably count 7, 8, 9 or 10 that seem to go to 0, and for the rest it's not so obvious. But the larger you take your n in this diagram, the more singular values would go below any given bound. Of course, some singular values are staying away from 0, like the big ones, they seem to go to 6, which must be the norm here. But infinitely many are going to 0, and that means it is not stably regularizable, which is the worst that can happen. So Minkowski theorem cannot do anything about that. Okay, I think that was enough examples. We had a stable one, a more Penrose stable one, 2 stably regularizable ones, and a last one that wasn't even that good.